need to heat something, you're using cogeneration to heat your water. That's one thing. The other thing, other part of a microgrid is storage. So storage is something new because it is not only a load, but also a source. It can act as both. So when you have excess generation, you can use the storage to store your power, your energy. And then when you need the energy, you can discharge your batteries and you can, you know, power up. But mind that when someone says storage, our mind immediately goes to batteries because that's what's been happening recently. But there are several other storage methods where you can store energy. Like for one example is flywheel. A flywheel is nothing but a giant rotary uh, wheel that is connected to, let's say, a motor. So during a normal time, the motor will rotate, and it is actually rotating the flywheel, the huge mass. And then, let's say the power goes off. What happens then is you leave the motor to rotate. This giant wheel has lots of mass, and it has inertia, so it keeps rotating. Now, what happens now is the motor turns into a generator. So you can use that stored energy in that flywheel now as to as generation source. So that is also a way to use flywheel. Now, flywheels are not extensively used everywhere. It's not like batteries. You cannot keep on discharging for a long time. But I will give you one use case that I have seen. I worked in a with a pharmaceutical manufacturing company. So they produce vaccines and all those critical stuffs. In their manufacturing process, losing power for just a minute would cost them millions because all their products that has to be maintained at certain temperature will go bad. So they have to throw away everything on the line and they have to restart the manufacturing. So it costs them $1 million or more. So that I've seen flywheels used there as a bridging source. So what would happen is in a normal, let me, okay, I'll keep switching um, pages here. So please don't mind, it's not just static slides. So I'm going to draw a power system. So we have the EB, electric board, or we call it electric utility, coming in. And we have, please don't mind my poor drawing skills. I'll try my best here. So this is utility 1 and this is utility 2. They're coming from different directions into this facility. And we have a main breaker for each incoming. And then you have a common bus bar. Then there's a tiebreaker. So these are all breakers. Usually breakers are represented like this, but in the US, this is mostly used for low voltage. High voltage and medium voltage are represented like this. So you have two sources already. On a normal day, you know, this one is normally closed, utility 1. Utility 2 is normally open, and the tiebreaker is normally closed. So what happens is, okay, let's also draw some of the uh, downstream loads. So you got some transformers. I actually forgot to put here, there are two transformers here in that facility. It's coming in at 40 kV and then it steps down to 13.8 kV. So everything down here all the way up to this place is 13.8 kV distribution. And this is T1, T2. This is medium voltage transformer 1, medium voltage transformer 2. This will take 13.8 kV to 480 volts. And we have other transformers that will take 13.8 48, 4,800 volts. So these are for high power applications. These are for regular loads. Now, need to use some colors here. On a normal day, you will have power flowing through this way because that's normally closed. There's no power here because this breaker is open and this entire bus bar is energized. You have power flowing through here. Oh, you know what? I actually forgot an important thing here. In that facility, we have a generator. So in fact, actually each bus has a generator. Because this is such a critical manufacturing facility, they have a generator for each bus. Now, going back to the scenario, we have this breaker closed, that breaker open, tie breaker closed. Let's say if you lose this utility, you're losing that utility, this breaker will open. So probably not do this. That breaker opens and your U2 breaker closes. So this happens probably in a millisecond, in 10 to 15 milliseconds, because there's a fast bus transfer uh, relaying application that senses the voltage drop in this side and immediately transfers to the other one. Now, if you lose the second utility, you're in blackout mode. So what happens at that time? The generators start up, they close the breaker here, and they transfer loads. They supply power. Similarly, if there's more power needed, you will have the other generator. Now, from the time the utility is lost and the generator to start and close the breaker on a dead bus, it takes almost from 6 to 10 seconds. Okay, that's a very short time, you might say, but in power system application, that's forever. That's very long time. And especially for this client, the manufacturing side, if they lose power for more than 5 seconds, they have to throw out the entire line that's waiting to be manufactured. So that's where I said they lose almost $1 million. So that's when they started to, they came up with the idea to add a flywheel. So like I said, it is a motor with a giant flywheel. Flywheel, like if you imagine, this as a motor housing, you have shaft, and then you got this giant flywheel. So it keeps rotating that. And so to give you in perspective how big this would be the size of a room. Like imagine you're sitting in a room, let's say 10 feet high ceiling. You see the flywheel that big. So that acts as a motor, and it keeps spinning the flywheel. And once both the utilities drop, what happens is this bus is dead, so there's no sources to synchronize, and the relay, it knows that these two breakers opened and it's not sensing any voltage on these two utilities, so it will close this breaker. So instead of importing power, now it will be exporting power because this is rotating and the motor turns into a generator. Now, how long this can go? This probably for 10 to 12 seconds. That's it. Such a huge motor and a flywheel is used only for 10 to 12 seconds. But that is critical to this facility. So what happens is, if you draw a graph, you'll have voltage, slightly fluctuating. Power system is not always at 50 hertz or 60 hertz in the US, slightly fluctuating. 59.95 or 60.05. But once the utility is lost, a very small dip, and immediately the flywheel catches up. The flywheel now is producing 60 hertz and the rated voltage. The voltage here is 13.8, so it'll be like 13.8 kV. And then that's just 5 seconds. Within 5 to 6 seconds, the generator would come online, and the generator will now synchronize with this rotary generator here, the flywheel. Synchronize and close this breaker. So then the generator will take on. So utility is down at this point, flywheel is down at this point, and generator is running. And while going back, so now we have this breaker closed, these two breakers open. When the utility comes back, the generator will do a synchronization, and then we call this as closed synchronization. Closed transfer, because we first close the utility into the system, synchronize the generator, and then once they're synchronized, the generator breaker will open and shut off, and you will have utility source. So what we did was we had seamless power, seamless transfer from one source, utility, to another source, the flywheel, to another source, generator, and when the utility came back, we went back to the utility. So a flywheel can also be a source of generation storage measures. So it's not just batteries. Let's clear this out. So does anybody have any questions? Was that interesting? Has anybody seen flywheels used before? Because this is the first place I saw, and I was like, wow, this is nice. This is a new thing that I learned today. So if anybody has experience with this, let me know. Going back to what a microgrid is, we have usually more than one source. So when I said the first example of having a rooftop solar, it was just one source. So it's very easy to control. So you have one source and one load, and that source will be the deciding authority. But when you have two sources, for example, you have two generators, okay, supplying a big commercial, let's say a mall, a shopping mall. Now you have two sources, and it is not connected to the grid.
Hello.
They will be starting to fight each other. So you would need to establish one as the reference and the other to follow the reference. And when you start adding other types of sources like PV and stuff like that, more complications that happen. So you usually need a centralized control. It's not always one centralized control. It could be divided into two or divided into three, maybe. I've not seen more than that. Uh, okay, I'm going to go on and tell you some of the places where I've seen microgrids and some of the places that I've worked microgrids. The first one, since I'm based out of Michigan. Michigan is a state in the U.S. Most of my projects for the past like 7.5 to 8.5 years was here. All the local projects I was involved. I moved on to another company called NEI. That is more like a bigger renewable power system design company. So now I'm doing projects in different states. So you'll probably see a combination of both in these examples. First one is the airports. Airport is one place where I've seen microgrids. So this airport is called Detroit Metropolitan Airport. What it has is it has 5 utility incoming. 2 come in at 120 kV and 3 come in at 69 kV. To give you a perspective, I actually have opened the map. Can you see the map? Can anybody confirm that you can see my map?
Yeah, we can see.
Okay. So this is the view of the map, and I'm zooming in to one side. So before that, sorry, there are two terminals, one on the north, one on the south. Okay. The south gets its own uh, utility source at 120 kV. Those are the two incoming. You have two transformers stepping down to 13.8. And then on the all the way on the other side, I don't know if I can mute them.
உனக்கு இப்போ என்ன பிரச்சனை நீ தானே வச்சிருந்த ரப்பரு அவனையும் விரட்டி விட்டுட்டு ஒன்றும் படிச்சும்
All right, that's better. Thank you. Uh, so yeah, like I said, on one end we have one utility coming in. Utility coming in. On the other end, you have three utilities coming in, three transformers. Okay. Now these were developed independently. Initially, this plant, the 369 kV utility coming in, has one steam turbine plant, and that was developed for uh, this terminal here, right behind it. So this terminal here, that's what it was developed for. And then for this terminal, these two actually terminals, there was this two utility incoming, and then we have three reciprocating engines, natural gas engine plants. So they were all developed separately. Now they were their own microgrid. But what started to happen, and this is something about how like even though you have three utility incoming, there is a possibility that you could lose almost every single one of them. So this was May 18, 2018. Uh, First of all, these utilities are coming from different geographical locations. They are not coming in a single transmission line. They're coming from different areas and coming into this airport. So if one tower falls down, let's say, the other side does not get affected because it is coming from a completely different area. So they are pretty physically isolated. But on that day, what happened, May 18, 2018, there was a severe uh, hurricane, and one of the towers like broke and fell down. Right. So one transformer was down, one utility incoming, and then coincidentally, a lorry, a truck, actually hit another pole, completely different area. It hit that pole, and the second transformer, the second incoming utility was also down. Now, the entire airport, I mean, this side of the airport was only powered by one transformer. Okay. Speaking of probability and chance, this power plant has a steam turbine engine. The steam turbine engine started because it takes some time, but still it started and it was ready to close in. But what happened was the breaker that was supposed to close did not work. So three complete random incident happened. One, a transmission line broken due to weather incident, another transmission line broken due to an accident, and a breaker failure happening. So now the generator is ready, but it cannot close in and cannot provide power. You are only using one transformer. So as the load started to pick up, the the utility was approaching, it was getting overloaded and load shedding started. So load shedding is when you have automatic cutoff of loads, which is not important. On top of that, in airports, you would also have local generators. Like, for example, you say this section of the airport would have certain local generators for few non-critical items. Um, And this incident happened. Nobody could do anything. And Finally, they had to wait for the transmission line to be repaired and the breaker here to be repaired. So it was a big lessons learned. They found a problem. Now, the other side of the airport, like I already said, we have this utility sitting there. And this is 120 kV. It's not a sub transmission level, it's a transmission level uh, line. So it is much more resilient to hurricanes or any other accidents, unlike the 69 kV. So that is a very reliable source. So what they thought, okay, can we connect this substation to this one? In theory, it is possible, but to make that happen practically, it's a very, very hard problem because you have a giant rotating steam turbine here, and then you have three baby engines. So they will try to fight. So now you have an actual microgrid. And as a power system engineer, we would go in and design the control system in such a way that you would put one uh, source as a reference and the other source follow that. So that was one interesting problem to connect two different existing substations, which were not designed to work with each other. And we brought in several people. Plus, this is an airport. It's not a private client. It's a government facility. So anything related to government moves very slow. There's lots of clearance required. You cannot shut down the airport. So you have to do it only during nighttime. So believe me or not, this project started in 2009 and it got commissioned in 2021. So the 2018 incident was just an expected incident because from 2009, people have been anticipating that, okay, what happens if one substation goes down? Can we power from the other substation? So that was in theory uh, available in paper, but nobody was doing anything. But after the 2018 incident happened, it took 3 more years to accelerate the effort. And then now these two substations are connected. So that was an interesting project. The other microgrid is college campuses. So college campuses, like a little bit bigger universities, have their own power plants inside their campus. So one of them is Eastern Michigan University, the other is University of Michigan. Uh, I did not show the one line of the airport because it has security clearance stuff. So I just showed you what's available in Google. But for this uh, university, it's Eastern Michigan University, we have, so this is one line. You have two incoming. Like I said, breakers are mentioned as a box, 52. It's a 40 kV line coming in. And then you have two bus bars tied by a tiebreaker. And you have also two transformers that steps down from 40 kV to 13.8. And then you have a power plant here. They call it a energy center. And you have a generator. Now, what's interesting here is that this generator, uh, they use the exhaust heat of the generator to heat up water, and that water is used to heat up, you know, like, like how you think about AC. AC is used to cool. Here, this exhaust heat is used to heat places during cold times. So that is called waste heat uh, recovery, WHR. So one, so now this is a microgrid on its own. So let's say you don't have these two utilities, you could run this generator, and then you could power up the campus. Now, what was interesting is the utility came up with the idea saying, okay, uh, you have a generator, okay, and the utility is getting stressed during peak summertime. So peak summertime is when everybody turns on their AC and the grid strains, and they have to cause load shedding and all those stuff. We all know about this. So in order to mitigate that, so the utility came up with an idea of why can't we take power from these microgrids? So they approached the campus. In fact, I should not say they approached the campus. The utility does not approach. The utility puts out a program saying, hey, if you have generation, you could enroll in this program and you could sell your power to us. That is one option. Or instead of selling, you can have your generation as standby. So whenever the utility calls for that generation, you should connect your generator. So imagine a very hot day and the utility operators are seeing that the load is going up and they might have to you know load shed some of the areas. So they would call this utilities saying that since you're enrolled in our program, can you start your generator? And the the college would start the generator. If it's already running, it will just synchronize to the grid and it will sell power. So thereby they can collect such small resources here and there, and they can alleviate problems like voltage drops, grid strains and stuff like that. What turned out to be very advantageous to them was while they are connected to the utility, during this peak period, they could still use that hot water to heat stuff. Now, you could ask me who's going to use hot water during summer, but there are other processes in the college like labs and other industries. There are industries inside the campus who use hot water for such, their processes. So in that way, that was useful. Um, so this becomes a double advantage for the college. They sell power and they get money, and using their waste heat, they use for heating whatever they want to heat. So instead of using electricity, they're using waste heat. So it's double advantage for them. So that's one cool uh, project that I saw, and I uh, worked on controls here, mostly protective relaying. The third example is a municipality. A municipality, we all know, it's a small section of a bigger city. But in the US, a municipality can be a separate city on its own, and that city will regulate everything: power, water, all those important utility stuff. That city will regulate. They will fix the rate of electricity. They will charge you for the water. So that's like a small, EB, like electricity board. Um, but how do they get power? They get power from different utilities, and they sell it for. So let me back to the drawing board. So in this case, so I'm not going to draw a one line. This is more of a geographical, representation. So you have poles and your electric lines coming in, maybe, just imagine, right? So this will be going all the way. And then you might have another transmission line going this way, completely two different utilities. This is utility number one, or EB, electricity board number one, and there is complete electricity board number two. And this was a 40 kV line, and this was a 120 kV line. So this is considered sub-transmission, the 40 kV, and this is called transmission level. So the city, it goes through the city. So what they did was they built a substation here, and they also built a substation here. So they would tap power from here, put a transformer, and then inside the streets, like you have seen electric poles in the streets, along the streets, they'll distribute that, along the streets. Several. Just imagine those are like, distribution lines. Similarly, in here from 120 kV, they would drop it down to some other level, and they'll. So what now? Okay, why is the city doing this? The reason is when you buy power from a high voltage, it's cheaper. As the voltage comes down, so this would be probably 13.2 kV, and this can be also 13.2 kV. Then every house will, like in the street corner, you have seen transformers. You'll have transformers here, and then that goes to your house. So they buy at a cheaper rate and they sell at a more, at a higher rate, and that's how they make money. Now, what they thought was, okay, we are buying power. They thought if you have rooftop solars here, you could, you can collect all those and you can actually sell power back to the grid if they require. Usually, sub-transmission and transmission level, they don't need power from such smaller local municipalities. But if it is large enough, they can actually support the grid when possible. So they also, it's not just rooftop. They also had some diesel and natural gas generators connected. So that is one way municipality makes money. So microgrids can also be used to make money. The other thing is something called as automatic reclosing. I don't know if anybody has experience or heard about automatic reclosing. It is basically, so let's say you have a substation, and then you have one line coming out. This is the overhead line that you see along the street, right? So you have lots of poles. Then you might have branches. So what they would do is, so let's say there's a okay, forgot to put that sinusoidal line is actually a fuse. So let's say this is a home, or this is a big factory. No, let's put some smoke here. So what you would do is, when you design the system, you would actually coordinate these. So it's called protection coordination. Some of you might already know about this. Basically, let's say this line is faulted. Maybe a tree fell on top of that. Okay, tree falls on top of the line and the line goes down. So that's a fault. Now, you don't want this breaker to trip, because if this breaker trips, this entire section is out of power. You don't want that. You want this nearest fuse to blow. Or if you have a recloser, that's even more advantageous. I'll tell you, a fuse, when it sees an overcurrent, it actually blows. It literally blows. It just explodes. And see someone raising a hand. Do you have a question, sir? Praveen? Maybe that was an accident. Okay. So you have a fuse that blows, and then this customer would call, hey, I lost power, and then the utility comes and fixes this. So how long will it take? It will take probably 3 to 4 hours. Instead, you can have a recloser. So I'll draw it here. A recloser, I'm gonna show it as a switch, but it is basically uh, a load interrupting or a fault interrupting switch. So when a fault happens, so let's put another factory here. So when a fault happens here, lots of current flow, like almost like 30,000 amps. So this recloser is capable of interrupting that. It opens it, and then it will try to close back automatically. And you can program this as power system engineers. If you know the tool, what tool to use, you can actually program this. You can program. So take in this case, a tree instead of falling. Okay, so let's go with this. These are the lines. So instead of a tree falling, let's say a branch grows out like this. And on a windy day, it's swinging and it is slowly touching and then coming out. It is grazing the line. It's not actually falling onto the line. It is just touching and coming out. So every time it touches, there is a short circuit happening. Then when it removes, the short circuit goes away. So in that case, you could actually use a recloser. So what would happen is when the branch touches, there's a fault, the recloser would open. And then when it goes away, there's no fault. The recloser can automatically close back in. If there's no fault, it will continue. It will keep on. It will be shut down. In the sense, it will be closed. But if the fault persists, let's say the branch is permanently on that line and there's a continuous fault all the time, it will open back again. So you will have something called a shot counter, meaning you'll count the shots, number of shots. Like you close one time, then it literally it goes boom, boom, and it opens, and then closes again, boom, it opens. So you actually time that, and you can create an incremental counter. And let's say after 3 shots, you keep it open permanently, and then you don't close it. So what you have done is you automated the process where the utility crew does not have to drive all the way down to this place and look what's happening. If it's a temporary fault, it will fix by itself. If it's a permanent fault, then it will open up, and the customer would call saying, hey, I lost power, and they will come and see what happened. Things have advanced now, so the customer doesn't even have to call. They will have communications sent all the way back to the substation saying this particular recloser opened. Dispatch a crew to see what happened. That's another interesting topic. So I can keep going on like this, but you could have seen me. I've just barely moved like 2 or 3 slides. So does anybody have any questions or any interesting experiences that you have had?
Participants, if you have any questions, you can shoot it to him.
All right. This means 2 things. Either you understood everything, every single thing I told, or you did not understand anything at all. So, but anyway, I'll keep going. These okay. I forgot to mention one more thing. Automatic reclosing. I want to show you what a recloser looks like. So that's a recloser. So see, this is how it's in substation. That's the line coming in, and then you have the recloser. That's phase A. You go to phase C. You have a line coming in here, then going out here. So this actually interrupts the fault, and that's on an overhead line. So that's how they typically look. So by using this recloser, you can actually reduce downtime. You can automatically close into faults. And this is the relay that we used in a company called Schweitzer Engineering Laboratories, as here. And this typically sits just underneath the pole. Just below this pole, you'll have this relay. and that will issue the control signals whether to close or not, and that relay will be doing the short counter increments. So this is an interesting thing. So using this DMS, you can actually map out your city, and you can map the lines, and you can, all these dots are where reclosers are. So you can you can open this from a remote location from your control center. You can see the status of the recloser, whether it's open or closed, whether it was open normally, or whether it was whether it tripped. So there's a difference between opening a breaker and tripping a breaker. Tripping happens when there's a fault. Opening is someone intentionally opening a breaker for some reason. So you can see all those states. You can configure them. You can just lay out on a map, and you will know exactly where those are, where the problem is, and you can send your crew directly to that place. So this is all stuff that you would see in a in a municipality microgrid. The other one, I'm going to go here quickly because so how long is the presentation? Do I have like half hour or 1 hour?
You can continue up to what you can, Pratap.
Okay, thank you. So the next one is engine testing plan. This is another interesting place. So what here they test engines of cars, car engine basically. So what they do is they draw power. They have several systems like compressor systems, this and that, and they try to measure the parameters in an engine. Okay, and the engine is actually run using diesel or petrol, whatever engine they're testing, right? So when the engine is running, they actually measure torque, and they also measure stuff that has to be measured using electrical systems. So in other words, the engine is actually producing power when they are testing it. So they need some, like, let's say if they want to apply brakes, they'll apply through electrical brakes. They'll use a resistor bank, and they'll apply resistance to the generator and see how the braking happens. Now, what they were doing is they were actually constantly producing power and wasting that power as heat in resistance banks. So let me quickly draw. So let's say, same way you have EB coming in, you have a transformer, then you have a giant bus, you have individual breakers. And then, let's say in this case, you have another bus bar, and you had these engines. So I'm showing them as generators here. So normally you would have power coming in and taken by these loads. These are offices, other loads in the same facility. Okay, and these would also require some power because their control systems and all their associated other equipments would need power. So they draw power. Okay, and when the engines are running, the engines would produce power. But the problem is they produce power and send it to this resistor bank. So resistor bank is simple. If current flows through that, it converts into heat. So basically that acts as a load to these generators. It's basically wasting heat, right? So we came up with an idea of similarly with the municipality example. Instead of wasting power here, you could actually send it back to the utility and sell the power, right? That was an idea. So I don't want to go into the details because we're getting late. But again, we had to come up with a control system, develop the microgrid around it to see when you can send power to the resistor and when you can power send out to the grid. And the grid had some controls. Like for example, there's a fault out in the transmission line here. So immediately what would happen is all these engines would start pumping out fault currents. We don't want that to happen. So what uh, the automation side of the utility did was they would have a control. They put a main breaker here that would come and trip this main breaker. So that was through an automation system. So now what happens, this microgrid is working along with the utility to supply power and get power whenever needed. So that was another project. So these are all my examples from Michigan. But recently, since I transferred to a new company, I'm seeing a lot of PV and BESS power plants, and some of them are even up to 500 MVA. So this is an example of saying microgrids are not actually always micro. They are becoming bigger now, because with easier control of inverters and bigger batteries, we are able to store more power and send it out. And mainly commercial players are entering the game. So that means a company would build a substation, a power plant, PV and BESS, and the PV would produce power during daytime. It will send power to the grid, and it will also charge the batteries. And during nighttime, the batteries will supply power. So thereby they can always, by supplying power to the utility, they are actually earning money. So it's a good, form of earning money if you have that much amount of capital. Okay, now only we're entering the phase of why do we need microgrids. So we talked about now what all the microgrids did in my few examples that I showed you. Apart from making a good business case, for money, it can be used for grid reliability. For example, let's say there's a cyclone or hurricane or a severe weather condition. If you have your own microgrid, let's say a collection of place, you can actually isolate that place and they can have their own power, while the utility can cut off power to that particular section. So the load or the stress on the grid becomes less. So you can have microgrids as a real reliable power source if you have the perfect combination of sources. Let's say you have a cloudy day, okay, and you have only PV as your source in your microgrid. If you only have PV, then you're not going to generate anything on a cloudy day. So it is a strategic design that you have to come up with. You should have probably a combination of diesel generators as well as PV. So when it's cloudy and night, you might need diesel generators. When it's a sunny day, you could use PVs maybe. So it depends upon the combination of sources. Next is resilience to grid disturbances. So when grid disturbances happen, like in the transmission level, usually there's a lot of voltage fluctuations and frequency fluctuations, and if that starts to cascade, it will start tripping off one plant from one plant to another, and then you could go into brownouts or even blackouts. So during that time, you could actually power up your own microgrids, and you can supply power to the local loads. And then black start. So okay, I forgot rural electrification. Places where it's very hard to bring overhead power lines or underground power lines, you could actually use microgrid and have your local distribution, and you can electrify your villages and places like where it's difficult, like mountainous terrain, where it's difficult to bring power. You can use this. Then black start. Black start is, let's say you have lost power, it's an outage, so it's blackout, and you need power to start, right? So if you start just one plant, and if you close the breaker, it's going to take the entire load and it's going to trip again due to overload. So you could sectionalize your distribution system and then you could probably just power up one part one by one, and then start closing in other parts of the distribution system. So that's called islanding. Um, Sorry, that's called isolation. Islanding is when you separate yourself, the microgrid separates yourself or itself from the grid, and they run on their own. Another thing I want to touch is grid following, grid forming inverters. This is actually inverters. Uh, so, like I said before, when you have multiple sources, you need one source to act as your swing bus, as a reference. That's the one source that every other source would follow. So, inverters, till like I would say 5 to 6 years ago, were just grid following, meaning they can't act as a master source. So you would need some other powerful source, and these inverters would follow, and they can start generating power. But nowadays, with new technology, the grid forming inverters have also come, which means a group of inverters would connect to each other, and they will form a grid. So it will become like a huge source. Like I said, the 500 MVA substation that I was commissioning before, uh, those have almost 225 MVA worth of battery storage. So what they would do, all the inverters can communicate amongst themselves, and they can form one huge source, and other small sources can synchronize to them. So that's one thing. And you can also support the grid. Like, you don't have to completely island yourself or disconnect yourself from the utility. You can still be connected, but take on some of the loads from the utility. For example, if the grid is getting stressed out, then you can start your diesel generator maybe, and synchronize, and then it will take some of the loads, so the grid's load would come down. So you can do that kind of load shaving, peak load shavings, and obviously make some money. So are there problems with microgrids? For sure, yeah. Like, controlling power flow, because now you have bidirectional power flow. Bidirectional power flow is not a problem because the entire grid has bidirectional power flow. It's not a huge problem. But now what's happening is the utility cannot control this power flow. For example, let's say you have PV, you know, rooftop solar on top of your house, and it's a bright sunny day. You're generating lots of power, and you're using most of the power from that solar array for your house, but you still have more power generating. Now you can choose, if you're connected to the grid, you can choose to sell it back to the utility. There's lots of regulations for that. The utility has to allow on all those things, but just going over the high level idea. So you can send back power, but the utility has no means to control that power. Let's say they don't want your power, they want to distribute or send it to a different area. They cannot do all those stuff. If they have a local power plant, like a big coal power plant or a nuclear power plant, they will have dedicated team, dedicated controls, and they can close and open breakers like they want to. But if you have such small microgrids everywhere, you would need some centralized control with the utility as one of the big players in that. You cannot have some private person, having a bunch of sources and connect to the grid. Then the utility cannot control those power flow. What about faults? Like I said, when a fault happens, all the sources contribute to the fault, which means, let's say your rooftop solar is connected to the grid and there's a fault out in the grid. It is not your mistake at all. It's somewhere happening somewhere, three roads down, three somewhere in other area. But still, since your PV is connected to the grid, it will push out fault currents. So now you don't know how to isolate which power. You have to design the system in such a way, and it becomes very complex. And always power system stability, because nowadays inverter-based resources are higher. Um, the controlling of the frequency and voltage is becoming an issue. This is an ongoing problem, actually. Everybody is working on this in the power system industry. Um, so when you have frequency and voltage control issues, you will definitely, go into power system stability problems, and then you'll probably open breakers you're not supposed to open, and it will trip itself off, thereby causing reliability issues. The last one is modeling. So I told you about grid forming and grid following inverters, which is good, but in order to study a system, you actually model the system. So in traditional systems, you would have a source and transformers and then circuit breakers and everything. You can actually model the source. Like even MATLAB has those models of synchronous generators, wind turbines, and everything. It also has inverter models, MATLAB and other big softwares. But to model an actual grid forming inverter is very difficult. I mean, still research is still going on, but I have not seen any software so far that is giving exact response of an actual inverter in simulation software. So those are the problems. But so far, I've talked just about microgrids. I have never touched about security at all. This is where the real problem comes in. Those all the other problems that I was talking about, many people have been working on for like 25 years at least. These problems, we know this will come when inverter-based resources come in, because they are not rotating machines. They don't have inertia. But the real problem now is cyber attacks or cybersecurity problems on microgrids. And not just microgrids. It's definitely in throughout the utility. But we are just talking about microgrids today. And it's not new either, because there have been incidents back from like I would say even 1993. People did using communication protocols. Back then, there were communication protocols were not that fast, but still they use communication protocols to trip some of the substations. So one such thing happened in California in 2020, and then in Texas. This is not actually a substation. It's a natural gas pipeline. So it sends natural gas to southern side of Texas. So a group of hackers took control of the instrumentation side. They could open up valves. They can close them, and they would push everything to one side, which is not desirable. You would want to control them in such a way that you want to maintain pressure, flow, and everything. But these people took control and started doing random stuff. And finally, they were asking some ransom money, and it involved a lot of problems like that. Similarly, this 2001 sewage release happened in Australia. So it was a waste or sewage treatment plant, and this particular employee was fired for some reason, and but that employee had access to their control systems. So he was just outside the fence of the plant, and he used radio controls to actually control some of the control system equipment, and then closed breakers, started some pumps that he was not supposed to start, and that led out sewage into an actual river. So it polluted a river for very, very for miles actually, and the city had to clean everything. So such things do happen, and I'm actually scratching my head. You can't see, but physical security is also happening. Like when you can ask me, like, what do you mean by physical security? Like literally, people jump over fence, go into substations, they break things, and they trip breakers. They don't know what those are, but they just do random stuff. Like for example, December 3rd, 2002, in a state called North Carolina, 2 substations were attacked. People were just shooting, like using guns. They shot the transformers. It started to leak, and it obviously protection kicked in and tripped off. But it left 40,000 customers without power. So they could see physical damages, like gates were broken, they entered, they cut the communication line, internet line coming into the substation. So there was no outside communication. So such things do happen. And then in April 2013, same, it's a transmission level substation in California. 17 power transformers were damaged. Like snipers were shooting from a long distance range into the substation, and it cost almost like $15 million worth of damages. So physical security is also a real problem in addition to the cyber security. Now, why is there a sudden interest in substations? Like I told, power systems have always been the most boring topic. Nobody even bothers to look at substations. Other than electrical engineers, nobody looks at substations. They don't even know what they are. But why is this sudden interest, and why are there attacks, more and more attacks nowadays in power system industry, especially microgrids? So one reason is electricity is now a critical infrastructure. It is not just like a need. Yes, we need electricity to function, but it is considered now critical, like hospitals, right? Hospitals are critical infrastructure. You need them. You want them powered all the time because you need doctors working on emergency situations. So like that, electricity is needed every single day. Plus, it is also running our lives, because everything we use nowadays has some sort of electricity backup or source. Number one, that's number one. Number two is communication networks. So communication networks have developed so much in the past 2 decades. Now we are inculcating, or incorporating communication networks into power systems. Now, when I say that, some of you might know that, but many people, like a general common man, would not know how is communications used in electrical substations. There's a lot of controls happening, protection happening through communications. And if someone goes and attacks a substation through networks, nobody can even see that. So physically, nobody's seeing any damage, but us power system engineers, we understand the problem of having communication networks as a means to hack a substation or cause damage. And then, like I said, technology we have taken granted, because our phones, everything is running on technology. For example, let's say you cut power to a very critical communication station. I'm not talking substations, a communication station where it communicates to satellite and stuff like that. If it's cut, or if you, let's say, if a part of the society loses GPS, you cannot actually go anywhere. Like, people are so much dependent on GPS and Google Maps, it will be very hard for someone to lose that and navigate. Same stuff with big data. Like, for example, when you punch in your phone to find a bus or a train, you get those information immediately, because there's lots of data centers processing those information. And those data centers and the communication towers that I just told use electricity. And we don't think about this because this is all common stuff that we use. But behind that is substations, a lot of substations that giving power to these data centers and communication networks. And also, taking down a substation can cause widespread damages. Like, for example, if you take down a transmission substation, you probably multiple cities will get affected. And think about hospitals and fire station and all other places where electricity is very much needed. You would lose power, and that can cause serious damages. and hence attack on such critical infrastructures is now termed as domestic terrorism. So at least the US, if someone gets caught, damaging utility stuffs, then it's going to be a very big problem for them. Okay, so what are the work in progress? And like I said before, I'm not an expert in this, but I will tell you, I'll share what I have been doing, or at least my company has been doing towards, for protecting against cybersecurity and physical security. So let's talk about cybersecurity first. First of all, careful design of communication systems. Communications in power systems is now a very integral part. It cannot be, moving forward, we will definitely have communication systems coming in, especially with IEC 61850, all those protocols, they all heavily rely on communication networks. So you're going to have, switches, gateways, and IEDs that communicate with each other, and designing that. So that's the first step, designing the communication systems in such a way, if it is if it is attacked, then you have means to rebuild your communications on the fly. Like, for example, how I showed the recloser. The recloser detects a fault, opens, and then closes back. If the fault is gone, it stays closed back. So it's an automation process, right? So it's same application, but in communication network, you can try doing, like, for example, forming a ring bus. Like if one side of the network is cut out, you would still have communication on the other side. There are protocols where it can sense a loss in communication in one network, and it can transfer to another network in a very small amount of time. So there are protocols like that. So you can use such kind of protocols. That's number one. Number two is network segmentation and isolation. So just like we talked about, how microgrids can be isolated from the entire grid, you could do the same with networks as well. When you design the network, so when we design a network for a substation, that network is local only to the substation. But let's say if one or two relays needs to communicate to a remote substation, for example, a line differential relay or a distance relay needs to communicate, we would have those two relays on a separate network. So the line relays and the rest of the relays would be on two different networks, but connected through some means of a firewall or a managed switch or a virtual LANs and stuff like that. So hardening firewalls is another thing, but I'm not too much familiar with that. And then regular updates and patching. And everybody might be aware of how you would get these regular updates for phones, for computers. That is because that is as a result of a lot of R&D happening in the background, research and development and advancement in the technology. So as they get those updates, and they also take lessons learned from mistakes that's happening. For example, once Amazon actually tried to push out one of their updates, and it dropped their entire western side of the US. So for an hour, Amazon was completely down. That's a big loss of revenue for them, and it's not a good sign. So they take those lessons learned, and then they incorporate those in the patches, and they send that in the upcoming updates. The other thing is advanced monitoring and detection. So I want to quickly go to this one, the same distribution management system. So you could actually design these system. For example, so that's a generator. Then you have a line, and that's a recloser. 500 amps, then another 500 amp recloser. Then you have a branching out. It goes to another feeder. So you can design systems like this, and then you can actually find where the problems are. So see here, this recloser has opened and locked out. So this is something SEL came with, so Schweitzer Engineering Laboratory. It's called fault location identification. What is S? It's separation. I don't know. And restoration. Fault location isolation and service restoration. Sorry. So such advanced monitoring and detection are also deployed nowadays, and we do that so that the people sitting in the control center don't have to just know the breaker status. So let's say in the 90s, where there was SCADA, but with slow protocols like Modbus and DNP. So you would still see the status of your breakers, what's happening with your switches, but they would not know why it tripped. Let's say a breaker tripped. That breaker indication will turn from closed to open, which is a good information, but they won't know why it happened. But with these advanced monitoring and detection with high-speed communication networks, you can actually know why it tripped. And then last one is employee and contractor training. This might seem very trivial, but this has been employed like throughout the US. No matter which industry you work in, every single employee or the contractors are trained mostly, how to not fall for cyber threats or cyber attacks. For example, don't leave your computer on and walk off, so that someone can come in and do things in your computer. So always shut down your computer. People in IT, people in like high finance companies, they have fallen for such attacks. Someone would send an email saying, "Hey, your boss is requesting you to click this link and approve something." They'll just go and click the link and fall for that attack. So such training even I have training in my company where they tell you, like, don't leave USB pen drives on your table, right? Don't take something that's fallen down and then like a USB pen drive and don't connect to a computer without knowing what it is. These are ways people try to trick in and try to initiate a cyber attack. Then for physical security, this is where IoT comes in very handy. The recent developments, you have you used to have cameras in substations. It's not a new thing, but those cameras would feed into a separate monitor, and the security person would be looking at the camera, right? It's not the power system operator. It's a separate security department which will be looking at the video feeds. And you know how cameras can be tricked into looping videos and stuff like that. So, but now with IoTs, you can actually have that connected to your power system monitoring software, and you can even detect, like, if there are people going in, detect movements. And there are also other sensors like smoke, gas, water, status of the equipment that you can see. You can actually make decisions based on that. Like, okay, nothing happened, like no fault has occurred or nothing happened. Nobody entered the substation, but my breaker opened. Why? So that could be someone hacking into your network and opening a breaker for no reason. So you can have detection systems like that. Badged access to substations. Every single client that I worked so far in the US gave me badged access to their facility. So without a badge that they gave me, I cannot enter their facility. So not just the facility, but the substations as well. Other thing is, when someone leaves a company, they would immediately take out the access. I told you an example that the employee being fired from a sewage treatment plant, and how they hacked the substation and opened the floodgates there. So to avoid that happening, you immediately revoke access to former employees. Okay, so we briefly talked about what's happening, what I have been doing in the cyber, at least in the microgrid area. But the real takeaway, this is what I want to conclude. I think I'm over the time, but the real takeaway here is there's a lot of work that needs to be done. It's not simple. I can keep on talking about examples that I worked on, and there's still more projects coming in. There's a lot of work that's out there. On the other hand, there are workforces that are retiring. People who were in the 60s, 70s, and 80s, who are like the pioneers and leaders in protection systems, SCADA systems, are now retiring. Okay, and as the new technology is coming in, seasoned engineers are not ready to learn new technology because they're already almost close to their retirement. So why should I learn a new technology now? I'll be gone in 10 years. So they're not ready to do that. Then other problem is there's a wide gap between a networking engineer, a power system engineer. A power system engineer in power systems can be divided as a SCADA engineer and a protection engineer. So when as a networking engineer, a networking engineer would not know what does a breaker mean. They would know about switches, they would know about routers, gateways, and all those stuffs, but they would not know anything about breakers or transformers, right? For them, transformers would be a movie. For SCADA engineers, they would not know what a trip means, what a differential trip means. They only know about SCADA stuff. Like, I'm seeing voltage, current, real power, reactive power, power factor, breaker status, and all those stuffs. But if there is a differential trip, they should know what that is. That's not happening because there's a separate department for that called as protection engineers. Those protection engineers deal with differential trips. If say Foucault's relay and transformer trip, a SCADA engineer would not know what that is. A protection engineer would know. On the other hand, a protection engineer would not know what a network switch is, what managed switch versus unmanaged switch, what is a VLAN. So there is a wide gap between all these sectors. And finally, technology is growing fast in power system industry. So I've been told by many people when I started my bachelor's degree that electrical industry is one of the most stable industry because nothing has changed for 100 years. You have the same motor, you have the same transformer, you have the same generator, and then there's distribution. So there's not much advancements, and there's not there's no new technology coming up every 5 years like in the IT industry. But that has changed now. Why? Because there's advancement in electronics, there's advancement in communications. So you have new technology coming up almost every 5 years. For example, the IEC 67850 technology started almost taking up in 2007, and edition 2 came in 2011. And from 2016, IEC 67850 has been used widely almost everywhere in the world. So such new technologies come up, and we have to keep up with that. So my takeaway is we can call anybody nowadays an electrical engineer or instrumentation engineer or software engineer or networking engineer. Everything is combining. Like I just said, a person who's working on power system should know networking, should also know SCADA, should also know protection of relay protection of the system. Only then you can bridge this gap. Then only you can fast forward all the implementing the new technology, hardening your substation, meaning hardening your grid, your networks. And then last part is about AI. I don't even want to go to AI. AI is a whole different beast, because that is even bringing everybody together: computer engineers, substations, mechanical, robotics, medical, everything. So this is my last slide. I promise, no more boring stuff. We need multifaceted workforce. We just don't need an electrical engineer. We just don't need an electronics engineer. We need who can work on networks, and also work on electrical stuff, and also write programs. Because believe it or not, I do everything, and that's what my beginning of the slide was. I worked on drafting, I worked on relay calculations, I worked on SCADA, I've done commissioning, and I feel there is not much people who are doing that. They're trying to isolate themselves, which would have worked back in the 60s, 70s, and 80s. But now we might have to know other other areas as well. We also need students to contribute as immediately as possible when they join work. We cannot have students, training for 5 to 6 to 7 years and then slowly taking over stuff. Because, like I said, the older generation, workforce is retiring, and we need to bridge that gap as soon as possible. So, two requests here. One for the academicians. If you give interesting real-world problems to the students, like I hope some of the examples that I gave you was interesting. So if you give such real-world problems, they would be intrigued to go and solve them. If you just teach theory and just slides after slides, they're not going to be interested. If you tell them that this is a logical problem that you need to solve, I guarantee that students would come in and solve the problems. And at the same time, we should also encourage multidisciplinary application projects. I think this is happening now, but back in my time when I was in college, this was not very much prevalent. So an electrical graduate should also work with a computer science student. They both should work with a mechanical student and come up with a solution for a real world problem. Second is for the professionals. Professionals, I would say we would have to tell the importance of the entry-level engineers, how important they are. Mostly it is considered like entry-level engineers are considered like, they don't know anything, they're just learning, and they'll take time to learn, and they have to be in the workforce for like 5-7 years to actually start contributing. But that's not the case. If you start telling them their importance, they will step up and they'll start contributing more right from the beginning. So teach as much as you know to them, share as much as possible your experience, but also be ready to learn new stuff from the new graduates. The new graduates come with a different kind of skill. Like, they would have a coding skill that might be applied in electrical industry, or some other skill that would not be related to electrical industry, but they bring in. So bridging that gap will definitely help fast forward, applying these technologies to actually protect our, grid. So with that, I'm finishing my, I said discussion, but nobody asked any question, but that's okay. If you want, if you have ideas, or if you want to discuss about this more, just feel free to contact me. Thank you.
Thank you, Pratap.
Thank you, sir. If you have any questions, let me know. I'll wait for a couple of minutes. If not, we can
Participant, please ask your questions.
If there is no question from participants side, Pratap,
Yeah,
Yes, ma'am.
yes,
hello.
really wonderful.
Ma'am, there is
That's
a
why
question from
we
a
are
participant,
always
ma'am.
insisting our students to do multidisciplinary projects as well as multidisciplinary research, which is very essential today, so that we can convert our conventional grid into smart grid. So
Yeah, definitely.
our grid is still 25 years or 50 years back what it was. That's why we have decided to give this topic as the FDP topic, and we are very proud to be, that is proud to say that Pratap sir alumni. Thank you so much. So we will continue tomorrow also, Pratap.
Will join.
At the same time, through the same link, we will meet again tomorrow. Thank you so much for
I have
your
a query, ma'am.
presentation.
If I'm audible.
Ma'am, there is a question from a participant. Sir, Jainul sir, you can shoot your question.
Yeah, first of all, thank you so much for the session. It was a wonderful session. Actually, I'm from a computer science background. I'm working on cybersecurity in smart grids. This is my research area. So I have one question. Just first of all, in case of smart grid scenario, what are the entry points where, for example, attacks like false data injection can affect? And the strategies which are applied for data networks, can it be applied for smart grid scenario or microgrid scenario?
Um, when you say data networks, can you explain a little bit? What do you mean by that?
The data networks are the computer networks, the networks that we
Oh,
use for data
in general. Yeah, yeah,
in
yeah.
general. Yes.
Right. So basically at the core level, both are same. You have a bunch of switches that is transmitting information from one side to another side. But in the electrical industry, it is not much prevalent. But the concept is still the same. We have some tools, at least that I am familiar with. Let me show one thing. Where is that? So okay, this one is called a software-defined network. So in general, um, so you would have a switch like this, a managed switch. You can program a switch and control the flow of data from one port to other port. But nowadays you're getting software defined networks. Like, you can actually write programs to actually control that. I don't know. I should not say I don't know. I'm pretty sure this must be in the data network world.
Yes,
But
it is there. It is there.
yeah. Yeah. So you know better than I. So I'm seeing this now in the electrical power system industry. So I am pretty sure the same concept would apply here. The only caveat is that whoever is working on the network side in power system industry should know the basics of power systems. Because I have worked with clients and they would tell me, okay, talk to this IT engineer if you want to set up the network. And I'll tell, okay, I have these relays, they all communicate Ethernet, and I want to go to this switch, and this is how the data flows. And then I would ask them, okay, I wanted to see the breaker status, and he would ask me, like, what is a breaker status? So then I have to explain that IT person what a breaker is, what it does. So this gap, is creating a problem between power system engineers and network engineers. So if you want to talk about smart grids or cybersecurity, that person who is involved should also know about power systems. That's the basic requirement. I'm sure since you are working in smart grid research, you should know the basics of power systems.
Yes, I'm learning, sir. Actually, how this to safeguard the network devices, there are techniques, and there are plenty of techniques to safeguard the network devices. My point was that, for example, in electrical network, there are plenty of IED device, intelligent electronic devices. They
Mhm.
take the data from the field devices, they collect it, and then they send it through the network, the data network. If the data is corrupted in the, for example, PLCs or in the IEDs, how to safeguard them? Is the same strategy applicable for those electrical devices?
Uh, what I have seen is there is something called quality of service. You might know in
Yes, sir.
switches. So the same idea is applied. This is just one of the protocols I'm talking about. This is not the entirety, but I have seen this done. So they check for the packets, and you have to program in such a way that you differentiate between a true packet or if that's an intrusion. Um, so like in the software SDNs, you can actually program them, and you can detect it. Another thing is not all the electrical infrastructure is connected like to the internet. You would have a separate network just for the substation and the yard. So you would get maybe from a breaker or transformer out in the yard, switch yard, coming into the control house. So you are only checking those packets, right? You're not checking the
Yes.
entire World Wide Web. So it becomes a little bit simpler when comparing to an actual IT network. So all you're concentrating is, I would say, 20 devices from the yard coming into your control house. Your control house has IEDs, probably
Yes.
40 or 50 IEDs. And it becomes a little bit simpler than connecting to the real world. And I can guarantee not the entire network in a substation is not connected to the uh, the internet. Only few certain points would be connected. And that's where I was talking about network isolation. You have to design your network in such a way that you're not sending all the information external to that substation. So I don't know if that answers your question, but those are my
Yes, sir.
exposure
Actually,
on.
I got some crucial ideas. And so one more, I have one curiosity. Many times I have seen that whatever intrusion detection techniques are there, they also detect the hardware failures, hardware due to hardware mismanagement or due to some hardware interference. Those data are also considered as attacks, cyber attacks, whereas they are not cyber attacks. Is there any mechanism to identify cyber attacks only? If there is, for example, if there is any error in the measurement, those error measurements are also considered as attacks. So I have tried many times and I got these wrong results. Is there any way to figure it out?
That's
Sir, I
that's why,
think
you know,
the cyber attack can possible only in the SCADA system, but cannot control of equipments because
Yes,
it's a hardware control. The security attack can happen in SCADA system, power purchasing system, but it's not possible with the control of the alternator transformers, everything, because it's a hardware control. Is it, Pradap? Is it correct or not? I don't.
that is actually that is correct, but that is changing now, and that's what I'm learning. For example, if you take let's search here. So what this device does is it takes in TTPT inputs and converts into digital bits. So I don't know if we have a good picture here, but you can see it can take hardwire inputs and stuff like that. So something like this would be in a transformer control panel, okay, in the yard. So the CTs and the contacts, the book calls relay, all other relay contacts, everything will be connected to this device in the control panel just near the transformer itself. And from this device comes out fiber, and it goes all the way to the substation. So all the CT wiring, control wiring going to the substation is now eliminated. It is only just fiber going to the substation. So in this case, that's what Jainul sir was asking. Let's say if you have error measurements coming instead of somebody attacking. So it's like, let's say you did not configure this properly and you have error message coming. How do you differentiate between an error message versus a real cyber attack? Right? I mean, I've not thought about this because again, when I think about like such error message, I'm just thinking from the equipment to the control house, right?
Okay, sir.
If anybody came in between from the control house to the remote control station, like remote control station will be outside the substation somewhere else, right?
Yes.
So if someone's coming in there and injecting error values, so instead of 440 volts, it is showing 1500 volts, let's say. So that's an error measurement we know, but we don't know how to distinguish. This is me thinking just now. I have not faced this problem, so I'm just thinking as I am speaking. The only way I could think is you could have parallel networking, where you could have the same data coming in a different branch. Okay, or there should be a way to detect if someone is intruding in the networks, not in the substation.
Or we can set a threshold. Beyond that threshold, we'll take it as a hardware.
So sorry to interrupt. We have separate session for differentiating those cyber attacks as well as false data injection, etc. We have 3 sessions exclusively for this cyber threat and cyber attack, cyber security in power systems. We have more discussion during those sessions. Participant, if you have any
yes,
you may ask.
It's okay. Actually, sir is working in that field. That's why I was a little bit curious to know about that.
Yes. We are having separate session for that. Cyber security in power systems, how to differentiate cyber attack and false data injection, and some other things, how to protect the grid against cyber attacks. We will have a separate session. Pratap sir?
Yeah, so those would be the people who are actually experts in
Yes,
that.
and that is in
field.
research level only, I think.
Exactly.
So.
Yeah, so
Still,
they're working
it's not
aggressively.
not actually practiced. So the people who are doing research will explain you during that session. So today, practical difficulties and practical demonstration has been excellently given by Pratap. Thank you, Pratap,
Thank you, sir.
Thank you, ma'am.
and thank you so much. Sir?
Pratap sir, thank you so much, sir, for your nice interaction. Actually, it is like a mini 60 hits tour to all our participants today. So it's really a wonderful journey, sir. We have taken your presentation to America. So it's like a live presentation, sir. So we'll catch up you tomorrow on this same time at 7:30 p.m. in IoT in cyber and power systems, sir. We're waiting for the next session by you in tomorrow's sessions. Thank you so much, sir, Pratap sir.
Thank you very much. See you tomorrow then.
Yes.